Welcome, everybody. Come on in, find a seat. We'll get started at the top of the hour. Okay, it is the top of the hour. And so welcome, everybody. My name is Alan Barr with COEH Northern California, and I'm sitting in for Michelle today. It's my pleasure to welcome you all to another presentation in our webinar series. If you're logging in today with your registration email, you will receive a link to an evaluation form that will qualify you for a certificate of completion worth 1 continuing education contact hour. You can join us next week for another webinar on the 15th, Wednesday, ergonomics research updates from the University of Michigan. You can register for that and many other upcoming webinars at coeh.berkeley.edu/webinars. For today's webinar, you will be muted during the presentation, but if you'd like to ask questions, please do so and enter them into the online Q&A box. We'll save some time at the end of the presentation to address those questions. The webinar is being recorded and will be made available along with past webinars on the COEH Northern California YouTube channel. Please like and subscribe to our channel to help us continue to grow it. Today's webinar, the title of the talk is Lithium Batteries, Understanding the Technology, Hazards, and Safety Risks. It's presented by our speaker today, Paul Harper, MBA. A little bit about Paul. He is principal and owner of Harper Consulting, LLC in Scottsdale, Arizona. He has over 35 years of experience in areas connected to product stewardship and sustainability, including environmental, occupational health, and safety and risk management. He served in corporate and senior consulting roles, working with numerous global companies across a broad spectrum of industries, most recently as Chief Sustainability Officer with a global leader in recycling and energy transformation. Paul's experience with batteries spans the life cycle of battery. He's worked in mining and extractive industries, producing battery raw materials for a global manufacturer of batteries, producing virtually every battery chemistry available today in data centers, telecommunications, and power management, defining the safe use of batteries, and finally in the recycling of batteries for metal value and plastic reclamation and reuse. And with all of that, it's my pleasure to hand the mic over to our speaker, Paul Harper.
Thank you, Alan. Hello, everybody. Thank you for spending some time today. We're going to go through some material for about the next 45 minutes or so. And then, as Alan said, at the end, we'll have 10 or 15 minutes available for questions that you may have during the course of it. And Alan will be keeping track of those. The things we're going to go through today is we're going to talk about, obviously, lithium batteries, but we're going to talk about lithium battery chemistries and technology. What does a lithium battery look like, and how does it work, and why is it hazard? And we'll talk about what those specific hazards are, what concerns us about them, so we understand what it is we're trying to protect against in their use. Then we're going to kind of look at different facets of battery use and battery management through the life cycle of a lithium battery, in particular when we use them, when we transport them, and when we collect and dispose of those through whatever mechanism. Then we'll move on to what are some of the applicable standards that we consider in the use and transportation, collection, and disposal of batteries. And in particular, we're going to focus on some of the fire standards that apply to those batteries. And last, we'll leave you with some resources and further information, places that you can get further information on these if you want to learn more. So with that, we'll kind of leap into this. Batteries, and more batteries. There are lithium batteries as well as many other chemistries in basically every form factor that you need. Every application is going to have a specific form factor. Up there in the upper left-hand column, we see a 12-volt car battery form factor. We see the, kind of AA, AAA, C form factors that we use lithium batteries in. We see the button cells that are lithium batteries, the CR batteries that go in everything from calculators to watches and different apparatuses to power them. And then, of course, large format storage batteries that you might see, these other large ones here that are going into large formats for battery storage. And bottom line is, a battery is an energy storage device. It's something that we put energy into, it collects that energy, and we use it to draw on when we need power, and then recharge those batteries when they're empty to give us more capacity and continuing capacity. And there's a multitude of existing and emerging battery chemistries. We've been using batteries for, centuries. And starting with the ones that most people were familiar with, the old lead acid batteries, and then of course NiCads and the nickel series of batteries, alkaline batteries that we use all the time, and that if you've got kids, you use way too many of. And then of course now we've moved into the lithium battery series, and the whole idea behind batteries and the whole advancement of batteries is the trade-off between energy density and the volumetric density. We want more power density in a smaller package. And these advancing as we move into the lithium series batteries, as we look further on down the line into metal sulfur, metal air batteries, those are trying to get more energy density in a smaller form factor, in a smaller package that enables it for greater use. The ones we're going to focus on today are the lithium batteries, and we're going to talk about both lithium batteries and lithium ion batteries, because it's important to understand the distinctions between them and the different hazards that we've got. Now, the next thing I want to talk about, though, is the different chemistries in there. And within, we see a number of different lithium ion chemistries: lithium iron phosphate, lithium ion with manganese, some with cobalt, some with thionyl chloride. But within any one of those, there's going to be multiple chemical components, and it's going to vary by manufacturer and by battery type. So you may have a lithium ion, lithium iron phosphate battery, or a lithium manganese battery that uses those base metals, but for any one battery, there's multiple components, and there may be very different ratios of the chemical components that are in there. And the thing about a lithium ion battery, importantly, that we'll talk about, is lithium metal itself is not a major component of a lithium ion battery. There is a small amount of elemental lithium in there, but very little. There's not a lot. The other thing that we want to recognize is that new chemistries are being developed and patented every year. There is a continual move to develop smaller, more powerful batteries and battery technology, energy storage solutions. And so new chemistries are being developed every day, and different components that enable those strategies, like a graphene matrix to give more surface area and create greater energy density in a battery, are being developed and deployed all the time. So what we talk about today are going to change over time, but these basic ones will still be out there in some form or fashion for the foreseeable future. So how do we use batteries? We use them everywhere. We use them in our homes. We use them in our businesses. We see them in electric vehicles and the emerging markets around those. We'll talk about those a little bit. They also get used in a variety of then commercial and industrial applications, data centers, power storage centers. These are very important areas. And then we get into battery, of course, battery manufacturers and battery recyclers. The blue arrow on the left there is meant to talk about the density of batteries that are present in a given area, because that'll emerge here as a theme in the level of hazard that you have to protect against. In a home, in a business, they're relatively low density. They're in this cell phone, they're in the computer that I'm using right now, but there's not any others in this room. In businesses, they're going to be relatively low density of the number of batteries and where they sit. But as we go down in these others, we get much more dense populations of these. In data centers, there's lots of batteries in the server racks that they're backing up. Power storage centers in even more denser configuration. Manufacturing, of course, and recycling, of course, even denser denser populations of the batteries. On the other hand, the proximity of those batteries to something that is combustible and the level of control that we've got over it is kind of in the opposite direction, right? In a home, there's a lot of combustible material in there. If that battery catches on fire, that is going to be proximate to that it can ignite and involve in a fire. But as we get into data centers, as we get into power storage centers, as we get into manufacturing and recycling, we've got lots more batteries, but they're a much more industrial environment. They are under much greater degree of control from a fire protection standpoint, and generally fewer combustible materials in that area. Those are both gross generalizations, but it does it's going to be an important factor as we talk about what the hazards are and what they can turn into. A little bit about battery technology. You know, batteries all are built pretty much the same way. There's an anode, there's a cathode. At the end of that, there's a positive collector and a negative collector that either collect electrons or discharge electrons. And then there is a separator and electrolyte. All batteries pretty much work this way regardless of the chemistry. And the things that we are concerned about are the cathode, the anode, and the electrolyte, because those are the components of the battery that are going to create both the energy that we are trying to harvest from a battery, but also create the hazards for it. And this is a kind of a rough, sorry about that. A rough idea of how these work, that, you know, when the battery is fully discharged, all the lithium ions are going over on the other side. When it's charging, we're returning them to the anode side. And then when we discharge them, those lithium ions come back across in the through the electrolyte as the transport vehicle and into the positive collection end of it. So that's kind of how the batteries work. And what we look at here then is, what does that mean? And this is where I want to talk about the difference between a lithium and a lithium ion battery. A lithium battery uses lithium metal in it, and the cathode is always going to have, it's going to be a varying metallic compounds in that anode, in that cathode, which is collecting it. The electrolyte is a lithium salt, but it's in a stable liquid or a solid or gel structure. It's not in a liquid structure. And it will always have lithium metal as the anode. Lithium metal is, what we're concerned about with lithium metal, of course, is that, like several other metals in that group, it is reactive with water and will ignite in the presence of water. Lithium ion batteries, on the other hand, will always have the cathode as a lithium salt, something like a lithium iron phosphate or a lithium cobalt oxide. That will form the cathode. They will always have an organic solvent, which is typically a liquid or a polymer gel. And then it will have a relatively inert anode that's a carbon cathode compound or some alloy of inert metals that we're going to be concerned about. But the things that drive the hazards of the battery have to do with what is in that battery that is going to catch fire or react or create the initial hazard. In a lithium battery, it's the lithium metal. In a lithium ion battery, it's the organic solvent, the electrolyte that we're looking at that's going to create the hazard in that battery and that we have to control during the use and management of those batteries. There's a lot of different battery chemistries out there. I mentioned this is just kind of a list of them. But so when you're looking at a battery, whether it's lithium metal or lithium ion battery, a lithium battery is always going to list the lithium anode, what's the composition of that, and the cathode. So it's going to have a lithium anode and it's going to have a cathode material that's made out of manganese oxide, carbon tetrafluoride, iron sulfide. It's going to be an Li- designation. Alternatively, a lithium battery is always going to be listed by the material that's in the cathode. So it's going to be the entire lithium salt compound that's in there that forms that battery. So that's how you look at it. If it's Li-, it's a lithium battery, has elemental lithium in it. If it's an Li whatever, then it's going to be a lithium ion battery. So what are the hazards that are associated with energy storage systems? This is really any energy storage system. This is not unique to lithium batteries, but it's more volatile with lithium batteries. Energy, electrical, mechanical, or chemical. Those are the 4 types of hazards that we've got. The ones that we're going to concern ourselves with the most here are going to be the energetic hazards, the reaction, a fire, explosion, burns that can trigger other items. We do, of course, have electrical hazards associated with any battery, any storage system that we can get from handling them. The mechanical ones, particularly if a battery pressurizes and would explode, then the shrapnel that comes out of it. And then chemical, we are worried about the toxic or hazardous substances that may evolve from a reaction, from a breach of a cell that people might be exposed to. But the most common hazard that we run into is this energy, and in particular, battery fires. And these are just, you can go on any website, look for lithium-ion battery fires, and we read about them. We read about them in computers and devices and phones and things. We see them in electric vehicles, house fires from battery charging, from lithium-ion battery charging that happens. And then, of course, we get the larger industrial fires. And this is what I meant by proximity to other items that are combustible. In a recycling facility or industrial facility, we've got this high concentration of batteries that has the potential to create a tremendous fire. In smaller units where we're only dealing with, one battery or one charger, there's a lot more combustible material around that can ignite as a result of that fire. And I don't know if you all saw it, but there was certainly in July 2021 a huge fire in Morris, Illinois, that resulted from over 100 tons of used lithium batteries being stored in a former paper mill warehouse. It was an unregulated facility. That's a clip of it. You can go on, Google this, take a look at it in YouTube. You also find one from Madison, Illinois, a recycling facility fire that burned, that went on. But this one in Morris, Illinois burned for over 3 days. forced evacuation of over 1,000 homes in the area. And the struggle with the fire department was how do we put this out? Because they were concerned that water or foam could cause the batteries to explode. And we'll talk a little bit about how we fight battery fires, but in a large scale fire like this, with a lot of elements involved, they eventually smothered it with 28 tons of concrete in order to isolate the batteries. And when you're fighting lithium fires and lithium ion fires, how you do that and what the fire protection systems you set up are really critically important. Well, why do batteries catch fire? And there's different failure modes that go along with it. First is the pressurization of the cell from off-gassing or failure to off-gas to release it, pressurizing that cell. That can just be triggered by normal reactions or by thermal runaway. We get a situation in a battery where that reaction that we're seeing between the positive and the negative, between the anode and the cathode, gets into a runaway and it generates heat. And then we get a cell rupture. When we get a cell rupture, that can either result in a fire just from the temperature that organic solvent was exposed to, or in the case of lithium metal, if it reacts with any water, if there's any water in the area to go there. Batteries generate heat, and we can have heat buildup in an area where the batteries are used or stored. A failure of the ventilation system in there can lead to a heat buildup, which also can trigger that thermal runaway. In there, damage to a cell, dropping it, hitting it with a hammer, hitting it with another object, that physical damage can trigger a thermal runaway. We overcharge them. We plug in lithium batteries to recharge. They are rechargeable, but when they overcharge, that again can create heat buildup within the battery and cell rupture and thermal runaway, as well as short circuits and voltage surges. The thing that when we talk about the international fire codes in a minute, one of the things that the most recent International Fire Code requires us to do in battery storage situation is evaluate these different failure modes, the consequences of them in that particular installation, and what are the mitigation measures that we apply to those. So that's where this in particular recognizing the potential for these different failure modes is important when you're thinking about how do I install them, how do I use them, how do I manage them. So let's talk about how we use them and how we manage them, and talk about the life cycle of a battery. I think Alan mentioned at different points in my career, I've been involved with every one of these from development to disposal and recycling of them. And the ones I want to focus on today, there's different issues associated with each of these every day, whether it's chemical storage, whether it's chemical use and packaging, transportation, how we install them and manage them and handle them, what is our emergency response protocol when they're in use, and at the disposal end, how do I deal with the packaging, the storage and transportation of them, as well as the ultimate method of recycling or disposing of that battery. And there's different regulations that are triggered kind of at each piece of that. That we need to take a look at that are going to come into play, that range from TSCA to chemical safety, DOT, and emergency planning, and then fire codes and fire protection mechanisms, where at the tail end of it, disposal, we've certainly got the RCRA and hazardous waste rules to be concerned about, as well as DOT rules for transportation of it, and ultimately, depending on how they're disposed of and the type of facility that you're using to dispose of them, the potential for circular liability related to that facility. The stages that we're going to focus on today in our discussion are not, we're going to kind of skip over what we do when we develop and build them, but we're going to focus on how we use them, how we manage them during their use and prior to disposal, and then at the end of it, how we collect and dispose of those batteries, whether by recycling or out and out disposal. So in each of these areas, we're going to kind of talk briefly about the requirements that go along with it, and then what are some of the best practices that you ought to consider when you're designing the application and the facility in which you're going to use them. Requirements, first and foremost, are going to need to follow fire code requirements. And that'll go to the hazard classification of the building. And that is in turn going to tie to International Building Code requirements for that building in terms of fire rating. It's also going to go to the maximum allowable quantity you have. How many batteries can you have in a given area? We're going to talk a little bit more about that, the fire code implications later. The particular fire code requirements are going to depend on where you're locating this and which version of the International Fire Code or the International Building Code that city or that fire district has adopted. That doesn't mean that if they're still have only adopted, I'm going to say the 2012 International Fire Code, that you shouldn't consider the 2018 and 2021 IFC revisions, but they may not be enforceable. They may not be strict parts of that. Also, you want to consider as a requirement your insurer requirements when you've got battery installations. And FM Global and NFPA really form the basis for the fire protection mechanisms that we have now. These are ones that recommendations by FM Global for their customers, temperature range that they have to operate in, the ventilation requirements based on the classification of the material, the sprinkler density, the stacking height, and packaging time limits, and the maximum amount of load stored in a location that go in there and how it's supervised. FM Global kind of specifies all this. If you are insured by FM Global, then it will be a requirement, an engineering practice. They'll require you to implement. If you are not insured by your property and casualty is held by another insurance, these are still well worth considering, even though they may not be a requirement, because FM Global is kind of the they're the gurus when it comes to fire protection. If you ever have the opportunity to visit their research center up at in Connecticut and go through a demonstration where they light a warehouse size storage rack of material together and look at the involvement of a fire and the different ways to put it out and different controls to put it out and the time it takes to put it out, it's well worth your time and effort. If you can't get there, you can actually see a lot of that on YouTube or Google it. It is impressive, and they do a lot of very good work. And I encourage you to take a look at that to understand what happens in a battery fire, and make reference at the end to FM Global's most recent 2016 reports on the subject, and that'll give you some more insight into that. Best practices, your SDSs for the batteries you're using are always going to have information that's helpful to you. You want to be sure that you've designated the proper PPE and equipment. We've talked a little bit about ventilation, regular periodic inspection of your batteries for heat, for swelling, signs that are for charge are important. In larger scale installations, your battery system may have a battery management system or a BMS in it, which collects that information and can be read at the battery unit or transmitted to your distributed control system to give you insight on that. As a best practice, when it's spent, you want to change it out. You want to take that out and then move it to a packaged area, because what we don't want to happen is for a used battery to enter into a runaway situation, even at a low state of charge. We want to get it out of that where it has an energized source to an energized connection so that we can safely manage it. It's when it breaches that we have problems. Up to the point it's contained, it's manageable. Once that battery cell breaches, then we have got active ingredients that are flammable or dangerous that are out in the open and exposed to other sources. So we want to find out when they're spent and get them safely packaged for disposition. But if there is an event, your facility needs to be prepared through a combination of sprinkler systems and designs like that to your emergency response to respond quickly for other elements of the batteries are around or other batteries themselves become involved in that fire. Battery transportation is pretty highly regulated. It's regulated by FSMA, which is part of DOT. Now, they don't regulate, they regulate ground transportation. Ground transportation either by vehicle or by rail, not by air. IATA regulates air. And the requirements around your transportation of those batteries are going to depend on the type of battery and the mode of transport. The lithium-ion batteries by far present the most complex shipping issues, and the regulations change in order to deal with that. Shipping by ground is relatively straightforward. It's subject to they're considered hazardous materials, and that are regulated under DOT regulations at Part 49, it involves the proper packaging, the proper density, the isolation of terminals that they're packaged in, and then of course the mode of transport, the amount of them that can be in a container. Shipping by air is more complicated for any battery, but in particular for lithium batteries. And on the right there is a table with the IAT requirements and the applicable DOT requirements relating to how we label it, what's allowed or generally prohibited in that, what has to be done in the way of testing of the battery before it can be shipped. What is the state of charge? And that's an interesting one, because in air transportation, they have to be shipped at a 30% or less state of charge. By ground transportation, they can be more fully charged than that and ready to go. But if it's by air, there's a definite prohibition on that. There's, as I said, packaging requirements that go attend each one, and then how do they need to be marked, and how do they need to be shipped. And if you've ever ordered something through Amazon that had a lithium-ion battery, it'll show up with a appropriate label on the outside of that package that designates lithium batteries and the hazards that are associated with them. What do we do with batteries now when they're done? We've used them in our facilities. We've taken them out of service. We now need to collect them either in our own facility or be collected by a handler and to another facility for doing this. A couple of points. Batteries are considered universal wastes under the Resource Conservation and Recovery Act. That's the RCRA is the act and the set of regulations that govern how we manage hazardous waste. So if it's a universal waste, they're still managed as hazardous waste, but there's a more streamlined set of requirements that attend how we manage those wastes and how we dispose of those waste than for other generators. But there are requirements that go along with each part of it. And in particular, if you transport batteries strictly for the purpose of disposal, you are considered a universal waste transporter. And that's going to trigger other requirements for you. So let's say you've got 2 or 3 facilities in the area, and you've got a load of batteries that you've collected at facility A. You want to put them in the back of somebody's pickup truck and move them over to one of your other facilities for consolidation. You're going to be considered a universal waste transporter when you do that. And so there's requirements that you are going to have to meet in terms of record keeping and management over the road in compliance with DOT requirements to do that. There are going to be restrictions, regardless of how you're accumulating those batteries, on the amount of time you can have and how you control the inventory of those batteries in there. So these are the universal requirements. You'll find them at in the Code of Federal Regulations at 40 CFR Part 266. And if you accumulate more than 5,000 pounds of batteries, now you are a large universal waste handler. So that'll trigger even additional requirements. But you do get some advantages for that. For example, under permit, the things you're permitted to do is you can sort batteries by type. You can mix batteries in one container. You can mix a whole bunch of button cells or a whole bunch of power tool batteries or those sorts of batteries in one container. You are allowed to discharge batteries to remove the charge from them at the site, as opposed to putting a more highly stated charge battery into that. That's not considered treatment, whereas under other types of the hazardous waste you handle, that would be considered treatment. You can just disassemble batteries into battery packs or individual batteries. And, you know, if you've ever seen a large format electric vehicle battery, it's big. It's like half the size of your kitchen table. And it contains, when you open that up, that container up, then there's lots and lots of cells in there. There is a there's a market for those used cells. You know, they will replace an electric car battery when it reaches about 80% of its recharging potential. If it drops below 80%, then it has to be changed out. That doesn't mean there's not still life left in many of those cells. They're not damaged. They're simply not recharging to the level they need to power that vehicle. And there's a market and applications for second use of those batteries that are out there. Don't try to do that at home on YouTube. You can find videos of guys that show you how to disassemble a lithium ion battery with a screwdriver and a pocket knife and a hammer. Please don't do that. There's a lot of hazards they don't talk about when you're doing that. And there are certainly concerns about doing that from a safety standpoint. Most battery recyclers that are recycling these on a large format or repurposing those have a very structured and controlled environment and process for disassembling that battery, testing cells, removing cells, placing them into their next use in there. Now, there's a difference when these are breached. If it's a breached battery over here when we're disposing of it, a breached battery is considered a hazardous waste. What do I mean by breached? I mean the container that the battery is in has physically been breached. The electrolyte is, or the anode or the cathode are exposed to the outside environment. Those are considered hazardous waste. If it's not breached, it's considered a universal waste. And then, of course, we've talked about the packaging and labeling requirements that go with those and how they're done. They're shipped on a straight bill of lading. If they're damaged but not breached, they can still be shipped if you protected the terminals and overpacked it before you've consolidated it to protect it from breaching. Again, that's what we don't want to happen. Some of the standards, I'm not going to read all these to you, but there's a variety of International Fire Code, National Electrical Code, International Building Code, NFPA standards that apply to the installation of use of batteries and energy storage systems in general. Then, of course, we talked about the transportation standards. There are also UL standards that attach to batteries that are being produced that you ought to be aware of. Some of the control, how the battery is made and how safe is it. And this is a list of the currently applicable UL standards around batteries and energy storage systems and equipment that may come into play, that may, if you're not manufacturing a battery, if you're using a battery, then you can see whether they comply with these as they have been. And that'll give you information on whether that battery has been produced in conformance with the currently accepted state of the art for these batteries. The key controls around it are our energy storage system, and these were addressed first drastically in 2018 in the International Fire Code. And there's a variety of things here where they're talking about key hazard controls in any energy storage system. What permits are required, what impact protection do you have to have? How do we store them, separate them? What are the maximum allowable quantities? What about UL listings that are required, battery management systems, on down through? I'm going to focus on a few of these here in more detail with respect to lithium batteries. The threshold limit for if you're using more than 20 kilowatt hours of batteries, that's the energy density of the batteries that you're using, then these requirements are going to apply to you. And it's going to require a hazard mitigation analysis for any unspecified technology, or if you've got multiple technologies being used in the same room, or if you want to increase the maximum allowable quantity of batteries that are in that space. That's going to require fire department approval. Notice that down here in the bottom in MAQs, the maximum allowable quantity for an incidental use room where we're just using them as part of the process is 100 kilowatt hours of that, or 100 kilowatt hours for technologies that are not covered by the code. If you've got over 100 kilowatt hours, you can apply for an increase in that over 100 kWh, but now it's going to require that that room comply with Group H hazard requirements under the International Building Codes. There are separations that are required. There's a location in the building that's required. For example, 75 feet above, less than 75 feet above the lowest level of fire department vehicle access. They want to be sure that the vehicles they've got in that jurisdiction can get above the fire if they need to fight, if there is one and they need to fight it. Arrays and spacing, it's got to be segregated into arrays of batteries that are less than 50 kWh each. So you're not going to be able to have, you're going to have to design your battery systems either in use or in storage where they're spaced out at least 3 feet away from each other and from any walls, and that's to prevent propagation of any fire event that might happen, to limit it to that particular array and to prevent it from spreading to other arrays. If you're storing them in an outside building, there's a requirement about how far you've got to be from the lot line and other buildings. And again, those same requirements for spacing apply in an outdoor building or an outdoor container as an indoor one. The batteries and equipment itself, there's information on UL standards that it must be listed by UL, or that it must be packaged a quart of in there. There are requirements around battery monitoring systems that are required and provided, fire suppression systems that go in there, and what is the commodity classification of the particular material. One thing that's interesting with lithium ion batteries is they're considered a class B hazard because of flammable liquid, because of the electrolyte, and because it's very flammable. But it's a commodity, because in a typical battery, the electrolyte in a lithium ion battery is going to represent something on the order of 7, 8, 9% of that total battery weight. But the remainder of it is largely going to be plastics, a few inert metals, and a lot of plastics. So that puts it into the commodity classification system that tells us how do we fight that fire. And normally with a class B fire, we wouldn't use water, right? Flammable liquid fires, we fight with foam or smother it with CO2, something to remove oxygen from the fire triangle so that it can't burn, and to keep from spreading it. If I've got a, gasoline fire on the ground and I spray it with water, I'm just going to move that fire. I'm not going to extinguish it. I'm just going to move it. With these mixed use, what's really burning after that small amount, relatively small amount of organic liquid burns is the plastic. That's what's burning. And in fact, both NFPA and FM Global specify use of water misting systems in order to attack that fire, both to put out the plastics and deal with a plastic fire, which is a class A material, and also to cool the other cells that are adjacent to it. If it's in a rack, if it's in packaging, what you don't want to do is not just catch the other cells on fire. You want to prevent them from heating up so that you start that thermal runaway reaction within the cell. So we're pouring water on there, not just to address the fire in the unit that's on fire in and of itself, to prevent it from spreading and other units being involved, but also to cool those other units so they don't actually start on fire by themselves. And some resources to follow up on that. There's been a lot of information here in a hurry. I apologize if I have talked too fast. I'm being mindful of trying to provide some time here at the end for us to take questions, but the International Fire Code and the International Building Code are important sources of information. There's digital codes. ICC Safe is where I've gotten mine, and there's some references there. For NFPA, there's some different reports out there. That second report on lithium ion battery and use assessment is available at that link, and it makes for good reading. Likewise does the technical report referenced here by FM Global that was first published in 2016 and was just revised in 2020. Other sources of information, because we're dealing with batteries, are the Battery Council International, which deals with the entire spectrum. That's a US-based organization that deals with the entire spectrum of batteries and issues associated with them, including environmental health and safety issues. And then the Portable Recycled Battery Association, PERBA, also has information in their website that is helpful in understanding batteries and safe use and best uses and best management practices around that. So with that, we've got, looks like about 12 minutes left for questions, and thank you all very much. We have covered a lot of information. We'll try to get through as many questions as we can in the time we've got left. If you have additional ones, my contact information is down there at the bottom. Feel free to reach out to me, and I'll try to be as helpful as I can be. Thank you very much. Alan, I'll turn it back to you.
Thank you, Paul. That was an excellent presentation. Thank you very much. Like you said, there was a lot of information there, and I'm sure we will have some questions. We have In fact, some coming in right now, and I will run through a few of these for you. What health, safety, and environmental problems do you anticipate when lithium or lithium-ion batteries are exported for recycling and disposal?
I think that with lithium batteries, if they're exported for disposal, certainly how you are disposing of them or recycling them when you're doing that are going to be an issue. You're worried about the end location of that. I think the reality is right now that most lithium-ion batteries are disposed of as universal waste at facilities that can accept those. They are not highly regulated batteries from that standpoint. If you've got a button battery, then you just like an alkaline battery, you probably throw it in the trash at home. So we do need to be concerned, just like anything, if waste is being exported, where is it being exported to, and what do we know about that before we consign our materials to them. The transportation is going to be the significant issue. What happens to a battery in transport, and how is it packaged or managed during that transportation event?
Thank you. What is the organic solvent you mentioned that's in the lithium-ion electrolyte?
Oh man, I knew someone was going to ask that.
That's a great question.
And it's a great question, and I'll look it up here, but I want to say it's DMAC is the name of the most typical solvent on it. I will get you that information, but you can look it up. But it is an organic solvent that it has a very low flash point, and I want to say it's DMAC.
Okay, and
I'll try to get that while we're.
That's okay. I mean, I think someone could Google that if they wanted to. Are there a variety of organic solvents?
Yeah, but I should know that. I should know that off the top of my head.
All right, let's jump into a couple more.
Yep.
All right, so are there any procedures available for responding to a bulging battery in a laptop computer? How is it safely removed and handled for disposal?
I think the way that you would do that is if you can remove the battery safely yourself, remove that. Obviously wear PPE when you're doing that, in particular safety glasses, because again, what you don't want to do is for that bulging battery to rupture due to an event. What you want to do is remove it from the sources. You want to tape the connecting spots, because that's what you don't want to happen, is for those to come into contact with each other and create an electrical connection. And then those types of lithium-ion batteries you can take to a low, if this is a home battery, then you can take those to a Home Depot, to a Best Buy, someone who manages those batteries, and they can help you dispose of them there at those locations. If you're an industrial operation, then it's a matter of overpacking that in an appropriate overpack container, and then consigning that to a collection service that's going to be able to transport those safely to the right place.
Okay, the next one, I didn't catch the context of threshold limit. I know you did mention it, but the question came in as in reality, how do you know if you're at a threshold limit? And can you give some examples? Do you recall the context?
Well, because every battery is going to have a rating on it for how many kWh are in that battery. So you're going to be able to look at the particular application that you've got for those batteries and understand what's the total amount, and what that is a trigger for, what that threshold quantity is a trigger for is, do I have to have authorization from my local fire department? And does that trigger the specific requirements of IFC 1206? And this is where when you're preparing any facility that's going to use large quantities of batteries, whether it's over the 20 kWh threshold or not. You want to be communicating with your local fire department. You want them to know. You want to know whether you have to have what approvals and permits you need to have for them for that type of facility. You also want them to know what's going on in your plant so that if something does happen, they can respond safely and appropriately to it. But through the, looking at the number of batteries you're going to have, it's 1 + 1 + 1 = 3. You'll know how many kWh you've got, and that's just the trigger for whether specific requirements of 1206 apply to you.
Is lithium versus lithium ion, is one inherently safer than the other? And which chemistry is more prominent, and what can we expect to see more of in the future? Or are they evenly distributed?
I would say the lithium ion technology is by far the more prevalent one, and the one that we'll continue to see more of in the future. The lithium metal one tends to be more specialized chemistries and batteries. Now we do use them in the little button cells, but most of those chemistries are used in specialized applications. Many of them related to defense or aerospace, and in other specialized industrial applications. So by far, I think the lithium ion is the predominant technology that we see and will continue to see.
And could you speak briefly to the inherent safety of one versus the other? Or are they relatively the same?
I think that inherently, I think the lithium ion would be viewed as safer. If I've got to think about what kind of event do I want to occur? Do I want it to be a burning organic liquid, or do I want it to be a reactive metal that reacts to water and requires presents even more challenges to fight? And I think the answer by and large would be a lithium ion battery.
Got you. Is there any off-gassing?
The thing about a lithium ion battery is they develop technologies like graphene is the one that comes to my mind, that increase the power density of a battery in a form factor. Lithium ion's more amenable to that than the lithium chemistry is, as I understand it.
Got you. And does off-gassing occur with lithium or lithium ion during the charging process?
Yes, any battery is going to have a small amount of off-gassing that goes along with it. In there, there's a controlled venting through the seal, but it's minute. It's not like if I think of batteries off-gassing, I think of old lead acid batteries that when you charge them or when they were in your car have a vent or vented and vent hydrogen gas, for example. You don't have that situation. The vent on one of these batteries is a safety valve, not something because it's a significant occurrence that they're trying to manage.
Gotcha.
Overpressurization.
Okay, thanks, Paul. We have a lot of questions here that we're not going to get to. I'll just throw one more here. What are the main challenges to lithium recycling? Why isn't more research, funding, support being directed to reclamation?
There's actually an awful lot of research and effort being devoted in the commercial space and in the funded space around lithium recycling. It's not as easily recycled as the materials that we have now. In recycling, you're trying to reclaim the base metals for reuse in that same type of battery chemistry or a similar battery chemistry. And those methods are largely hydrometallurgical as opposed to pyrometallurgical, but they're just in the developmental stages of that. And I think a lot of that's been because traditionally there hasn't been the volume of batteries or the demand for the recycled metal material that made it commercially viable. And that's changing as we look at the future of EV batteries in particular, and the commitments companies have made to produce all EV vehicles by 2035. We look at the amount of lithium and other supporting metals that are going to be needed to build all those batteries. We're going to need recycled content. There was a good report by the International Energy Agency, IEA, a couple of years ago that looked at that issue and projected that by a foreseeable point in the future, we would actually need about 40% of the metals needed to meet EV battery demand would have to come from recycling. So that is being developed. There's a lot of work going on in this space to commercialize it. It's being able to commercialize it at scale and that's economically viable and competitive.
All right. Well, thank you again, Paul. That was an excellent presentation. And thank you, participants, for your questions. Apologies to you if I didn't have time to get to them. You can learn more and register for our upcoming events at coeh.berkeley.edu. And you can also subscribe to our YouTube channel, where you can find recordings of previous webinars and other events. As a reminder, if you logged in today with your registration email, you will get a certificate for completion worth one continuing education contact hour. If you have any questions for us here at Northern California COEH, you can drop us a line at coehce@berkeley.edu. That's coehce@berkeley.edu. Thanks again to our presenter and to everyone that joined us today, and we will catch you on the next one. Thank you, Paul.
Thank you very much, Alan. Thank you, everybody.
Bye-bye.